Okay, folks, this one's going to go a little bit faster than the previous ones. I went ahead and did the example, and we'll just talk about it. So, if you haven't read the question yet, if you haven't tried the problem, go ahead and pause the video, read the question, try the problem, and then we'll work through it. So take just a moment to do that, or as long as you like, actually. Okay, so let's go ahead and take a look at this problem. Here we have two cars. They start at the same point, and they're traveling 60 miles. One's traveling 60 miles per hour to the south, whereas the other one is traveling west at 25 miles per hour. Okay. So I went ahead and gave us a little, here's a compass. What's going on? We have the first car, the first car's heading south at its rate, and the next car is heading to the west at its rate. Okay. So I went ahead and just zoomed in on just that one side of it. So I'll let you take a look at that. Of course, always pause the video as you need to. So our first car is heading south, and the second car is heading west. That forms a nice little right triangle here. And of course, our question is how fast is the distance between the two cars increasing after a period of 2 hours? So I just went ahead and labeled some of the important information here. For example, car A is heading south at 60 miles per hour. Car B is heading west at 25 miles per hour. Between these two, you have the hypotenuse of this right triangle. So the question really is, what is dc dt? That is, how quickly is this line's length changing, given what we know about how these other two lines' lengths are changing. So this one required a use of the Pythagorean theorem. So I started with that. Again, just pause the video as you need to. I started with the Pythagorean theorem. I implicitly differentiated both sides. And notice that this gave us this expression involving C prime, which is what we're trying to solve for. Okay. Notice that all these factors have a factor of 2, so I canceled them out. And then this is always true, right? A prime in this problem, this car is traveling at a fixed 60 miles per hour. So I went ahead and substituted that in. B prime, again, is the same is fixed for this problem. The second car is heading west at 25 miles per hour. I didn't incorporate the negatives into these. You could have, but you'd get the same answer, and it's just easier not to deal with them. Okay, so for our specific instance, though, the question isn't what is C prime always, although you can look at that and you'll find kind of an interesting result when you do. The question wasn't what is C prime always, but instead it was what is C prime after 2 hours have passed. So notice that after 2 hours have passed, the westward traveling car is now 50 miles from the starting position, and the car that is heading south is now 120 miles from the starting position. How did I get there? Well, if the southern driving car is traveling at 60 miles per hour, and it's been doing this for 2 hours, then it has traveled 120. So that's where I got that from. Okay, similarly, this is 50. So then I simply used the Pythagorean theorem and found that C in this instance was 130. So this is our specific triangle that we're looking at, given that we know that this is increasing by 25 per hour and this is increasing by 60 per hour. So I took this equation right here that's always true, and we went ahead and plugged in the specifics of our point in time, where the distance we've traveled to the south is 120, and the distance the car traveling to the west is now 50 miles from the starting position. And so we've now got everything we need, and we solve for C prime. I'll let you do that work, and you'll see that C prime is 65. That means that the distance between the two cars is growing at a rate of 65 miles per hour, and this is technically after 2 hours have passed. But you should think about that, because I believe that actually that rate of 65 doesn't change. All right, we'll go ahead and stop it there.